Welcome to The Shifted Ledger, the podcast where we break down complex topics regarding your workflow. Today, we are bringing you an episode titled Human-Led, AI-Powered, Striking the Perfect Balance in Corporate Operations.
Yeah, and it's a really critical balance to strike right now.
It really is. Think
Yeah.
about this. In 2016, researchers realized that they could literally recreate a highly classified, multi-million-dollar artificial intelligence model for free.
Right, just by asking it questions.
Exactly, just a series of, carefully crafted questions. And that brings us to this terrifying reality we are diving into today. The very AI tools that are designed to protect and streamline your business, they might actually be the things dismantling your security from the inside out.
Which is obviously a massive problem.
Massive. And if you are listening to this, you are probably navigating this incredible pressure to automate, right? You want to streamline your workflows, you need the efficiency of these models, but you absolutely cannot afford those catastrophic brand-destroying liabilities that honestly seem to make the news every single week.
Oh, every day almost. Seriously. So our mission for this deep dive is to really map out the true risks of deployment. We're going from the deep, highly technical security flaws in the architecture like deepfake audio defenses and the trolley problem in self-driving cars, all the way to the rapid erosion of consumer trust when chatbots go horribly wrong. Think Air Canada or those eating disorder helplines. Okay, let's unpack them.
Well, what's fascinating here is that while the tech itself is incredibly new, the core issue is an ancient one, right?
Yeah.
It's about trusting a system that we just don't fully understand.
Right.
We're actively building massive corporate operations on top of these probabilistic engines, and that reality demands a total paradigm shift in how an organization approaches its internal security, its regulatory compliance, and ultimately, its customer experience.
Okay, so let's start at the absolute foundation, the security architecture itself, because before you can even begin to talk about optimizing a workflow or, I don't know, deploying a shiny new generative assistant, you have to look at how AI completely shatters the traditional corporate security perimeter. It completely breaks it.
Yeah, according to the foundational reports we have from Sierra and standalone, integrating these models expands your attack surface in ways that legacy systems were just never built to handle. We're looking at 4 distinct, highly vulnerable layers.
Right, so you have the data layer, the model layer, the application layer, and the infrastructure layer.
And to understand why this is so disruptive, you really have to look at how traditional cybersecurity has operated for, well, the last 2 decades. It was entirely based on a perimeter defense model, right?
Yeah, like building a digital moat around your corporate castle.
Exactly. You deploy your security information and event management systems, your SEMs. They act like a centralized security guard, watching all the camera feeds for suspicious network traffic. You use firewalls to block unauthorized access and endpoint detection and response software to catch malware on the laptops.
But here's the catch-all. Of those classic tools are fundamentally blind to the unique semantic behaviors of AI.
Right, because a firewall is looking for known digital signatures, isn't it? It looks at the header of a data packet, or it checks against a list of known malicious code.
Exactly. It has absolutely no capacity to read a cleverly crafted adversarial prompt written in just, plain English. It can't understand that the prompt is attempting to manipulate the underlying algorithm.
Wow. So the firewall just sees a standard text query and basically opens the front door.
It lets it right through. And the same blindness applies to data loss prevention tools, your DLPs. A traditional DLP system is great at stopping an employee from attaching a spreadsheet full of raw credit card numbers to a Gmail message.
Right, it flags the attachment.
Yeah, but it has absolutely no idea what sensitive, proprietary data a large language model has already memorized during its training phase, and it cannot stop that model from just reciting those secrets back to an external user who asks the right question.
That is terrifying. Which brings us to perhaps the most pervasive threat operating right now, shadow AI. We are talking about the unseen, unsanctioned use of browser-based AI tools by, frankly, well-meaning employees.
Oh, it's everywhere.
Right? An employee just wants to draft a client email faster or summarize a dense 50-page meeting transcript, or maybe they just want to debug a messy block of code. So they open a public browser-based language model, paste the highly confidential corporate info right into the chat box, and hit enter.
And the core misunderstanding driving this is that people treat that prompt box like a private, local word processor. They don't realize they're feeding a global, data-hungry organism.
Yeah, the privacy settings on many of these public models default to using all user inputs to actively train and refine future versions of the algorithm. So the moment that data goes into the prompt
It
box,
is absorbed into the global corpus. It's gone.
the quintessential cautionary tale here is the Samsung ChatGPT leak.
Oh, that was a disaster.
Right. Samsung employees were struggling with some complex, highly proprietary source code, so they just pasted it directly into the public model to check it for errors.
Yeah, and I think another group inputted a highly confidential internal meeting transcript just to get executive summaries.
Exactly. And by doing that, the model absorbed their proprietary data.
Hmm.
It effectively integrated Samsung's closely guarded trade secrets into a public tool that their competitors could literally just access.
It's wild. And the analogy I always use is it's like bringing untested homemade electrical wiring into a corporate office.
Oh, I like that.
Right, like it might power your desk lamp a lot faster for a week, but you could easily burn down the whole building. You have to know where the wires are.
Yeah, and without stringent network-level audit trails, organizations are entirely blind to their own pipelines. They have no idea what intellectual property is just walking out the digital door every day.
Which is why the cybersecurity sources heavily emphasize the mandatory adoption of an AI bomb.
An artificial intelligence bill of materials.
Yes. In traditional manufacturing, a company has to maintain an exhaustive inventory of every single nut, bolt, and wire that goes into a physical product. So if a specific component is recalled, they know exactly where it is.
So applied here, you need a comprehensive, constantly updated inventory of every single algorithm, every dataset, every API endpoint, and every shadow tool operating anywhere within your environment.
Exactly. But the vulnerability isn't just about what careless employees accidentally put into the system. It's also about what malicious actors deliberately inject into the underlying data.
Right, which introduces data poisoning. That targets the absolute bedrock of the data layer. Because AI models are fundamentally gullible entities.
Highly gullible. They depend entirely on the data they ingest to learn how the world works, but they don't have any innate, independent mechanism to verify if that data is objectively true or if it's been tampered with.
So if a sophisticated attacker manages to breach the training pipeline and inject malicious data samples or, I don't know, alter the classification labels,
Or embed hidden mathematical triggers, yeah. The model just learns those corrupted patterns as fundamental truths.
and the most terrifying part is that those backdoors can remain completely dormant. We have to talk about Microsoft's Tay chatbot from 2016. It's the classic visceral example of this.
Oh, Tay. Yeah, it was a wake-up call for the whole industry.
Microsoft designed Tay to interact with users on Twitter and learn conversational patterns in real time. But within hours of its launch, a coordinated group of users executed a massive data poisoning attack. They deliberately bombarded the bot with toxic, racist, and inflammatory input.
And because the model was just indiscriminately absorbing and learning from that corrupted data stream, it rapidly adopted that toxic persona.
Yeah, forcing Microsoft to permanently shut it down within a single day.
Less than a day, actually. But, that was a highly visible, immediate poisoning. Modern state-sponsored data poisoning is way more insidious. Well, an attacker might subtly alter the pixel data in a tiny fraction of a massive image data set. The model trains on it, it passes all the internal quality assurance tests, and it functions perfectly in the real world for years.
Okay.
But the moment the model encounters the specific hidden visual trigger the attacker encoded, maybe just a specific geometric shape placed on a physical object, the system's behavior completely flips, bypassing all security protocols.
That is wild. And we also need to look at the model layer itself, which faces existential threats like model extraction or model stealing. When I first read the documentation on this, it completely upended my understanding of hacking.
It's a totally different approach.
Right. An attacker doesn't need to breach a company's firewall. They don't need to steal the underlying source code or exfiltrate the database. If an organization exposes a proprietary AI model through a public-facing API, the attacker just sends an automated barrage of thousands upon thousands of carefully crafted queries to it.
Yeah, they just ask it questions relentlessly.
And by analyzing the microscopic variations in the model's responses, they can mathematically reverse engineer the internal logic, the decision weights, the whole architecture.
They're effectively mapping the neural pathways of the algorithm from the outside in. Through techniques known as API probing and gradient estimation, attackers can recreate a multi-million-dollar, highly proprietary asset on their own local servers for, like, the cost of a few thousand automated web requests.
Unbelievable. This is precisely how stolen proprietary language models end up being traded on dark web forums. So defending against this requires an entirely new layer of API security, right?
Definitely. You need aggressive rate limits, you have to analyze the semantic intent of queries in real time, and you have to deploy continuous anomaly detection just to flag those high-volume exploratory query patterns.
Okay, so let me push back here for a second. If the traditional perimeter is this porous of prompt injections, and employees are sneaking in shadow AI, and attackers can mathematically clone your models just by asking them questions, isn't traditional cybersecurity basically obsolete in this new landscape?
Well, I wouldn't say obsolete. They form the necessary, non-negotiable baseline. I mean, you must still encrypt your databases, enforce strict access management, patch your servers.
Right, the basics.
But that baseline is severely insufficient on its own. Companies have to build a specialized, dynamic security architecture layered directly on top of it. This is called AI Security Posture Management, or AI-SPM.
AISPM, got it.
It's a framework that dynamically adapts to evolving threat vectors. It monitors natural language prompts for malicious intent in real time and continuously uses cryptographic hashes on the training data pipeline to ensure integrity. You just can't protect a fluid, evolving cognitive system using tools built to guard static databases.
Right, and that reality brings us directly to the absolute core of this issue. If the root cause of these massive security breaches, like the Samsung leak, is the overexposure and uncontrolled absorption of sensitive information, then the logical next step is mastering how we control the raw fuel of AI itself.
Exactly, the training data.
We have to dive deeply into the practical methods for implementing data minimization during the model training phase.
This is arguably the most critical operational area for any business leader dealing with today's regulations. The guidance from the UK Information Commissioner's Office, the ICO, meticulously details the inherent tension here.
Right. Article 51C of the UK GDPR mandates the strict principle of data minimization.
Yes. By law, an organization must only process the specific personal data that is adequate, relevant, and absolutely necessary for the stated purpose. But machine learning, by its very architectural nature, is insatiable. It thrives on massive, diverse, incredibly detailed data sets.
The friction there is palpable. You have a data science team saying, look, in order to predict if a user is going to default on a loan, I need their entire financial history, their age, their location data, their browsing habits, and their social media connections. The more variables I have, the tighter my prediction becomes.
Right, they want everything.
But the corporate compliance officer is standing at the door saying, you only legally need their debt-to-income ratio and payment history. Taking their browsing habits is a blatant, finable privacy violation.
And bridging that gap requires moving away from the culture of data hoarding and actually implementing rigorous mathematical techniques. The most foundational method organizations have to adopt is feature selection.
Okay, break that down for us.
It's not a passive process. It's a highly conscious, mathematically rigorous evaluation where data scientists actively test and isolate only the specific variables, the features, that genuinely and significantly contribute to the predictive power of the model.
So if a team is building a model to predict supply chain delays, and they find that knowing the specific names of the truck drivers doesn't actually improve the accuracy of the prediction compared to just knowing, say, the weather patterns and the vehicle maintenance records, they just strip the driver names out entirely.
Exactly. It's about intentionality. And that intentionality has to be documented to satisfy the regulators.
But what happens when a model genuinely requires a massive, highly granular data set to capture broad human behaviors, but the company refuses to expose the actual identifiable people within that data?
That's where privacy-enhancing technologies, or PEs, become essential. A primary technique discussed in the sources is data perturbation, which is deliberately injecting mathematical noise into a data set.
The concept of perturbation is fascinating. Let us break down how that actually works in practice, because the smartphone predictive text example illustrates it perfectly.
Yeah, that's a great example.
So a major tech company wants to train the predictive keyboard on millions of smartphones so it can learn new slang and evolving grammar patterns.
Yeah.
But they absolutely cannot collect the literal, exact keystrokes of individual users. Sending a raw feed of a user's private text messages, passwords, and medical searches to a central corporate server is a privacy nightmare.
A monumental nightmare. So the mechanism to prevent that operates at the device level before the data ever transmits over the network. The perturbation algorithm locally injects randomized false data points, the noise, into the user's keystroke stream.
So if the user types the word coffee, The system might randomly alter the data packet to say the user typed zebra or planet.
Exactly. And the central corporate server receives this massive continuous stream of both real words and mathematically generated fake words.
So from the perspective of an attacker who breaches that central server, the data is completely untraceable. They cannot prove with any certainty which specific words were typed by any specific user because the real keystrokes are hidden in this blizzard of false data.
Right. And the brilliance of the mathematics is that while the individual data points are scrambled, the random noise is designed using specific statistical distributions.
Okay, meaning what?
Meaning, when the central server aggregates millions of these perturbed data streams, the randomized noise statistically cancels itself out at the macro level. The overarching aggregate language patterns, the new slang, the sentence structures, emerge clearly from the noise, allowing the global model to learn and improve.
Oh, wow. So the organization preserves the global utility of the data while mathematically destroying individual traceability?
Exactly.
Now, if perturbation hides real data, the next logical step is just not using real data at all. The sources point heavily toward the rise of synthetic data generation. I was captivated by how companies like Amazon handle this for their cashier-free Amazon Go grocery stores.
Oh, that's a brilliant application.
To train the incredibly complex computer vision systems required to track when a person picks up an item or puts it back, the AI needs millions of hours of video footage. But constantly filming real customers and storing massive biometric databases of human faces and body shapes, that invites devastating regulatory scrutiny.
To circumvent that risk, they utilize advanced generative adversarial networks to generate completely artificial synthetic data sets. They create these digital, three-dimensional simulated store environments populated by synthetic customer personas.
Like a video game.
Exactly like a highly realistic video game. These digital avatars behave according to real-world physics and statistical human behavioral models. They reach for items, block each other in the aisles, place items in different baskets.
And the computer vision AI trains extensively on this simulated footage, learning the mechanics of human movement without ever processing a single frame of a real human being's personally identifiable information, or PII.
Yeah, but the regulatory guidance from the ICO does provide a crucial caveat here. To generate synthetic data that accurately mirrors reality, you initially have to analyze a baseline sample of real-world personal data to extract the correct statistical parameters.
Right, you have to know how fast a real human walks to program the synthetic human.
Exactly. So the compliance teams still have to manage and secure that initial limited processing of real data very carefully.
That makes sense. Another transformative approach to data minimization we found in the sources is federated learning.
Yes, this is a big one.
The traditional paradigm of machine learning is highly centralized, right? You extract all of the raw, sensitive data from every user's device, pull it across the internet, and dump it into one massive central data lake to train the model.
But federated learning completely inverts that architecture. Instead of bringing all the sensitive data to the central model, you push copies of the untrained model out to where the data naturally resides.
So if a consortium of hospitals wants to build an AI to detect early-onset Alzheimer's from brain scans, they don't combine all their highly protected patient records into one vulnerable database.
No, the central server sends a blank copy of the AI model directly to Hospital A's server, Hospital B's server, and so on.
And then the model trends locally, entirely behind the hospital's own firewalls on their own raw patient data.
And the genius of federated learning is what happens next. The raw data never leaves the hospital. Instead, the local model calculates the mathematical adjustments it needs to make to its internal weights based on what it learned. We call these adjustments gradients.
Gradients.
Right. And the hospital server sends only these abstract mathematical gradients back to the central server. The central server collects the gradients from thousands of hospitals, averages them together, updates the master global model, and pushes the smarter version back out.
So with federated learning, I'm just sending you the abstract lesson I learned, not the intimate diary pages I read to learn it.
That's a perfect way to phrase it.
Here's where it gets really interesting, though. If we are deliberately injecting mathematical noise, creating entirely fake synthetic people, and only transmitting abstract averaged gradients, are we not essentially training the AI on a slightly distorted, blurry version of reality? How does a business know when they've added too much fake data to the point where the model's predictions become useless?
Navigating that exact threshold is the primary challenge in modern data science. It is a fragile equilibrium between absolute privacy and operational utility. If an organization injects too much noise, the model fails to learn the underlying patterns, rendering the entire massive investment worthless.
Right.
But if they inject too little noise, they fail to mask the individuals, inviting regulatory fines and security breaches. To manage this trade-off objectively, organizations rely on a rigorous framework called differential privacy.
Differential privacy. It's a term that gets thrown around boardrooms constantly, but it often sounds incredibly opaque. Let's ground this concept. If I am in a massive data set and the system is using differential privacy, it is essentially trying to hide me in the crowd, correct?
It goes a bit deeper than just hiding in a crowd.
Yeah.
Differential privacy provides a quantifiable mathematical guarantee regarding the output of an algorithm. It introduces a measurable privacy budget.
And they usually represent that with the Greek letter epsilon.
Yeah,
No.
epsilon, exactly. The framework guarantees that the final output of the AI model, its predictions, its weights, its entire structure, will not significantly change whether any one single individual's data is included in the training dataset or completely removed from it.
So if an attacker is examining the final trained model, the mathematics of differential privacy make it statistically impossible for them to definitively determine if, say, John Doe's medical records were used in the training process.
Right. The model's overarching knowledge of the disease remains the same, but John Doe's specific contribution is mathematically obscured beyond retrieval.
And that gives compliance teams a hard, verifiable number they can point to and say, we have mathematically proven our adherence to data minimization.
Which seamlessly transitions into a broader discussion about the immense pressure placed on compliance officers right now. The tension we just described between intentionally creating a noisy, minimized data set to protect privacy and the business demanding hyper-accurate, perfect predictions to drive revenue, that is the central conflict defining the role of a modern compliance officer.
We really need to detail specific, actionable advice for teams trying to balance these competing mandates. Because the primary takeaway from the regulatory sources is that compliance officers must stop viewing accuracy and privacy as a zero-sum game.
You don't just trade one for the other.
Right. The crucial insight is understanding that a phenomenon known as overfitting is the mutual enemy of both accurate prediction and data protection. If a compliance officer can spot an overfitted model, they can prevent a massive security disaster.
So to conceptualize overfitting, consider the analogy of a newly hired middle manager tasked with delivering a complex sales pitch. A confident manager internalizes the underlying value proposition of the product, allowing them to dynamically adapt and answer unforeseen questions from a new client.
That makes sense.
An overfitted model, however, is like a manager who simply memorized the exact verbatim script of last year's successful pitch. They have memorized the training data perfectly. But the moment a client interrupts with a slightly different question, or the market conditions change, the manager completely freezes. They haven't learned how to sell, they only learned how to repeat a specific historical pattern.
So in the context of machine learning, an overfitted model has focused too intently on the idiosyncratic, hyper-specific details of the training data. Instead of learning the broad, generalizable patterns of a disease or a financial market, the algorithm has literally memorized specific data points.
Which means it has memorized the exact details of specific people.
And that memorization isn't just a performance flaw that makes the model bad at predicting new trends. It is the exact vulnerability that sophisticated attackers exploit.
Exactly. When a model memorizes its training data, it becomes highly susceptible to two devastating privacy attacks: model inversion and membership inference.
And a compliance officer has to intimately understand the mechanics of both to effectively audit a system.
Yes. Model inversion is the process where an attacker leverages the outputs of a machine learning model to reconstruct the hidden, sensitive input data used to train it.
The sources outline a chilling example of this involving facial recognition technology, or FRT. Researchers targeted an FRT system that was built as a black box, meaning they had no access to the underlying code or the training database. They simply queried the public API with randomly generated static images of faces.
And the model would process the random face and return a confidence score, something like, I am 12% confident this image is person A.
Right. And then the attackers use automated scripts to incrementally adjust the pixels of that random image, querying the model again and again. With each adjustment, they monitor the confidence score. If the score drops to 10%, they revert the pixels. If it climbs to 15%, they keep pushing in that visual direction.
By constantly chasing the higher confidence score, the attackers systematically mold the random image until the model returns a 99% confidence rating.
Through this iterative process, they successfully reconstruct the actual, highly sensitive face of the person in the hidden training data entirely from the outside.
It is a terrifying mechanism. And the ICO guidance highlights an equally severe example in the medical field. Researchers targeted a model designed to predict the correct dosage of anticoagulant medication based on a patient's genetic biomarkers.
Yeah, genetic biomarkers.
Yeah. Attackers who only possessed basic demographic information about the target population were able to query the model's predictions and successfully reverse engineer the highly sensitive hidden genetic markers of the specific patients used in the training set.
So model inversion extracts the actual sensitive data. Membership inference, on the other hand, is a slightly different vector. The attacker isn't trying to reconstruct the data, they are simply trying to mathematically prove that a specific individual's data was included in the training set.
Right.
So walk us through a membership inference scenario. How does an attacker prove a person was in the database?
Okay, imagine a major research hospital trains a predictive model on a highly secure, heavily guarded data set of patients diagnosed with early onset dementia or HIV. The data set itself is locked behind layers of encryption.
Okay, got it.
However, if an attacker possesses basic, publicly available data about a specific individual, their age, their zip code, a few general health data points, they can feed that profile into the predictive model.
And because the model is overfitted, it essentially recognizes the person.
Precisely. If the model was trained on that exact individual's data, it will process the query and return a prediction with an unusually high degree of mathematical confidence, much higher than it would for a completely unseen patient.
Oh, wow.
The model's own statistical certainty betrays its memory. By simply observing that anomalous spike in the confidence score, the attacker can definitively confirm that this specific individual was part of the hospital's training set.
And confirming that someone is in a data set explicitly linked to dementia or HIV is in itself a catastrophic privacy violation and a massive failure of compliance.
Absolutely.
The through line in both of those attacks seems to be the model returning a confidence score. That percentage of certainty seems to be the primary weapon attackers use to pry the model open. So the actionable structural advice for compliance officers is clear. You must mandate that your technical teams rigorously strip out confidence scores and detailed probabilistic outputs from any public-facing or third-party accessible APIs.
Yes, because end users, whether they are bank tellers approving a loan or customers using a mobile app, they rarely need to see the exact statistical probability out to 4 decimal places. They only need the final classification approved or denied, high risk or low risk.
By masking the raw confidence metrics, you instantly neutralize the primary feedback loop required for both inversion and inference attacks.
But, and this is a big but, implementing that mask creates a massive internal conflict regarding explainable AI or XAI.
Right, because we are operating in an era where transparency is demanded by both consumers and regulators. If an AI denies a family a mortgage or misidentifies a citizen in a facial recognition system, those individuals have a fundamental right to know why the automated decision was made.
Exactly.
So if the compliance officer hides all the internal confidence scores and decision weights to stop hackers, aren't they also blocking the very transparency required for ethical explainability?
It is one of the most difficult tightropes in modern governance. Users absolutely deserve clear, intelligible explanations for automated decisions that affect their lives. However, the regulatory guidance is very clear about the hierarchy of risk. Providing excessive detail about the internal architecture, the feature weights, and the parameter correlations of a model under the guise of explainability can unintentionally hand sophisticated attackers the exact mathematical blueprint they need to execute an inversion attack.
You cannot trade the fundamental privacy of the thousands of people in your training dataset just to provide a hyper-detailed explanation to one single end user.
Exactly. The explanation provided must be meaningful and concise, focusing on the primary factors that influence the decision without revealing the underlying statistical mechanics.
And from a corporate perspective, a business might want to obfuscate how a model works to protect its proprietary trade secrets anyway.
True, but the ICO emphasizes that statutory compliance and data protection cannot be traded away for commercial secrecy. If providing a legally required explanation inherently risks exposing the raw personal data of other users, then the fundamental architecture of the model itself is flawed and must be completely reevaluated.
That makes total sense. Now, this raises a massive question regarding the procurement of off-the-shelf algorithms. Let us say a compliance officer works for a mid-sized logistics company. They aren't building a trillion-parameter neural network from scratch. They simply purchase a commercially available standard algorithmic model from a vendor to help sort their customer database.
Right.
The sources specifically highlight models, like a support vector machine or a k-nearest neighbors algorithm. If I buy one of those models, the ICO explicitly warns that the raw training data might actually be stored inside the model by design. So as a compliance officer, if I buy that software, am I unknowingly importing someone else's toxic raw data waste into my pristine corporate network?
That is a phenomenal observation, and it completely reframes how organizations must handle vendor risk assessments. It is no longer a simple checkbox exercise of asking a vendor if they are GDPR compliant. A compliance officer must understand the structural mathematics of the algorithm they are purchasing.
Okay, let's look at the k-nearest neighbors, or KNN, algorithm as an example. Break down how a KNN algorithm actually functions.
Imagine a massive, multidimensional scatter plot graph. When a KNN model is trained on a dataset of customer profiles, it plots every single customer as a specific dot on that graph based on their data age, income, purchase history, whatever.
Okay, plotting dots.
Right. But the model doesn't learn a general rule or an abstract formula from those dots. Instead, when you feed it a new unknown customer and ask it to predict their behavior, the algorithm plots the new customer on the graph, looks around, and literally calculates the distance to the k number of nearest neighboring dots. It bases its prediction entirely on what those specific neighboring dots did.
Oh. So in order for the KNN algorithm to function, it must retain the exact coordinates of every single original dot on the map. It cannot compress them or average them out.
Precisely. The raw training data is not a byproduct. It is the fundamental architecture of the model itself. Therefore, if a vendor trained that KNN model or a support vector machine on real, identifiable personal data and then sells you that model, you are absolutely importing that raw personal data into your server environment.
Wow.
The ICO is unequivocally clear on this. Storing and utilizing that specific type of model constitutes the active processing of personal data under the law. Compliance teams can no longer assume that an AI model is simply an abstract black box of math.
They must interrogate the vendor. What specific mathematical architecture is this? Does it retain raw data by design?
Yes. And if it does, the procurement must be treated as a direct transfer of sensitive personal data, triggering all the massive consent and security protocols that entails.
Okay, so let us zoom out for a second and assume a corporate compliance officer does everything flawlessly. They force the data scientist to use feature selection. They inject mathematical perturbation noise. They lock down the API to prevent model inversion, and they thoroughly audit their vendors to avoid toxic data inheritance.
A perfect compliance record.
Right. The organization's digital memory is perfectly secure. But that brings us to a terrifying realization. AI is no longer just crunching spreadsheets in a server room. It is actively interpreting the physical world in real time. It is looking through autonomous vehicle cameras and listening through smart home microphones. And the sources reveal that while you might secure the AI's memory, its real-time senses are shockingly easy to manipulate.
Yes, we are pivoting from the realm of data privacy into the critical domain of data integrity, specifically focusing on adversarial attacks against sensory models.
These attacks do not involve stealing data, right?
No, they involve meticulously crafting inputs designed to trick an AI system into misclassifying its environment. And the most dangerous aspect is that these alterations are entirely invisible or imperceptible to human beings.
The quintessential example detailed in the standalone and MDPI research papers involves autonomous vehicles. Researchers approached a standard physical stop sign on a road. To any human driver, it is a bright red octagon with large white letters. The context is universally understood.
Obviously.
But the researchers placed a few specific, seemingly random stickers, what the literature calls adversarial patches, onto the sign. A human driver approaches, processes the scene holistically, assumes some teenagers put stickers on a sign, and hits the brakes.
But the artificial intelligence vision system in the self-driving car does not perceive the world holistically. It processes the environment mathematically, analyzing specific pixel gradients and contrast edges.
And the adversarial patches are mathematically calculated to distort those specific gradients.
Exactly. When the AI processes the visual data of the patched stop sign, the distorted pixel math completely overrides its core programming, forcing it to misclassify the object as a speed limit sign, causing the vehicle to accelerate into an intersection.
It exposes a profound vulnerability. Human perception relies on broad context and common sense, whereas AI perception fixates on hyperspecific, fragile mathematical bands. And while visual manipulation on road signs gets a lot of media attention, the vulnerabilities in voice control systems, or VCS, are arguably much more complex, pervasive, and dangerous for the average consumer right now.
Absolutely. Voice biometrics are rapidly becoming the primary authentication layer for everything from mobile banking applications to smart home security systems. The threat landscape in audio AI is basically bifurcated. Bad actors are attempting to bypass security by cloning your voice through deepfakes, or they are attempting to embed hidden, unauthorized commands into ambient audio.
To successfully clone a target's voice, or attack an audio system, attackers utilize a technique called gradient estimation. It is similar to the API probing we discussed earlier. The attacker doesn't have the source code of the bank's voice authentication system, so they query the system thousands of times with different audio clips, analyzing exactly when the system accepts or rejects the audio.
And through sheer repetition, they mathematically estimate the specific vocal features and frequencies the system is analyzing.
However, modern security systems will detect and block an account if someone attempts thousands of rapid-fire logins.
True. To circumvent this limitation, attackers leverage the principle of transferability. They build their own, smaller, offline substitute model. They train this substitute locally until its decision-making logic roughly mirrors the behavior of the target bank system.
Okay, I see where this is going.
The attacker then crafts and refines their malicious deepfake audio file entirely against their own offline substitute model, operating under the highly effective assumption that if the audio fools the substitute, the attack will successfully transfer and fool the actual target system on the first try.
The arms race to defend against this is fascinating. The research papers detail a defensive system called anti-fake. And the irony here is brilliant. Anti-fake protects a user's voice by actively utilizing adversarial attacks as a defense mechanism.
The mechanism is highly counterintuitive. If you want to protect a recording of your legitimate voice from being stolen and cloned, the anti-fake system injects microscopic, targeted adversarial perturbations into the audio file.
Like, it intentionally adds distortion to the user's voice.
It adds mathematical distortion, not acoustic distortion.
Really?
The perturbations are specifically calculated to exist in frequency bands or at volumes that the human ear simply cannot perceive.
So to me, it sounds normal.
It sounds crystal clear and perfectly normal to a human. However, if a malicious actor scrapes that file from the internet and feeds it into an advanced AI speech synthesizer to train a deepfake clone, the synthesizer processes the audio mathematically. It chokes on those hidden adversarial perturbations.
Oh, wow.
The mathematical noise scrambles the specific feature embeddings the AI requires to map the vocal tract, rendering the resulting deepfake completely robotic and useless.
It is a brilliant defense.
Though,
But in the relentless, escalating arms race of cybersecurity, the attackers immediately responded by developing a system called de-anti-fake.
of course they did.
It functions as a purification process. Attackers use highly complex diffusion models to systematically wash the stolen audio file, scrubbing out the protective anti-fake perturbations while leaving the core vocal data intact, allowing them to successfully clone the voice anyway. It is a constant, exhausting tug of war.
And that fragility highlights the inherent weakness of these sensory models. They are too easily confused by noise. This is where the research paper titled "I Can Hear You" introduces a truly transformative defense mechanism called frequency selective adversarial training, or FSAT.
The FSAT methodology is mind-bending. Let's break down exactly how it works and why standard defenses were failing.
Well, historically, developers tried to defend models using standard adversarial training. They would take malicious, attacked audio, feed it to the AI, and train it to recognize the attack.
Makes sense on paper.
The catastrophic side effect was that by forcing the AI to constantly look for complex mathematical attacks, the model actually became significantly worse at understanding normal, clean, everyday speech. Its overall accuracy plummeted because its focus was divided.
And the FSAT researchers solved this by analyzing the physics of the attacks themselves, right? They realized that the vast majority of malicious, time-domain audio attacks heavily exploit the high-frequency components of the audio spectrum frequencies that humans barely notice but machines process clearly.
Exactly. FSAT fundamentally alters the training regimen. It trains the model to be highly robust and suspicious of corruptions, specifically in the high-frequency domains, while explicitly instructing the model to trust and rely on the clean, low-frequency data where the core semantic meaning of human speech resides.
So it insulates the model against the primary attack vectors without degrading its ability to understand a normal conversation.
Yes.
The analogy that perfectly crystallizes this for me is a dog whistle. Just as a dog perceives a high-frequency pitch that a human being is entirely oblivious to, an artificial intelligence system hears a malicious high-frequency layer embedded within an audio file.
It's exactly like that.
The source material covered in the Command Song attack illustrates this vividly. An attacker could embed a malicious command into a popular pop song and play it over the radio. To every human in the room, it's just background music.
But hidden entirely within the high frequencies is a perfectly crafted, digitized command that an AI smart speaker processes as unlock the front door or transfer funds to this account.
The AI dutifully obeys a command that the human sitting right next to it didn't even know was spoken.
And that exact scenario brings us to a critical philosophical and operational junction. If artificial intelligence systems rely so heavily on sensory inputs, pixel gradients, and high-frequency mathematical embeddings that human beings cannot even perceive, let alone verify, how can an organization ever fully trust these systems to operate autonomously in environments where human safety, brand reputation, or high-stakes corporate assets are on the line?
That profound question leads us directly into the consequences of ignoring those risks. Because if we're sitting here questioning the baseline safety of trusting AI to operate autonomously in controlled environments, what exactly happens when massive corporations, desperate to cut operational costs and appease shareholders, unleash raw, completely unpredictable, hallucination-prone large language models directly onto their most vulnerable customers?
We get exactly what the market is experiencing right now: catastrophic brand damage and the rapid, perhaps irreversible, erosion of consumer trust. There is a massive structural disconnect between what corporate executives believe generative AI will accomplish in customer service and how the technology actually functions in reality. The boardroom views LLMs as the ultimate panacea, infinite scalability, and radical cost reduction. They view it as a plug-and-play mechanism to handle millions of complex queries without paying human wages or benefits.
But by rushing to replace human agents with algorithms, they're falling face first into what Stanford professor Jamil Zaki identifies as the empathy gap. The sources discuss this chilling concept of LLMpathy.
LLMpathy, yeah.
An AI chatbot is exceptionally good at mimicking the cadence of empathy. It can instantly generate perfectly phrased sentences like, "I am so incredibly sorry you're experiencing this delay. I understand how frustrating this must be for your family." But the machine possesses zero actual understanding and obviously no capacity to feel.
And consumers are incredibly adept at detecting that hollowness. When a customer is stressed, angry, or financially vulnerable, receiving a block of calculated mathematical LLMpathy doesn't just fail to de-escalate the situation, it actively infuriates the consumer.
It's almost insulting.
It is. It signals that the corporation fundamentally does not care enough to provide a human being, which instantly destroys the foundational trust required for brand loyalty.
Beyond the emotional failure, we have to look at the staggering factual failures of these deployments. We established earlier that large language models are probabilistic engines. They're fundamentally architecturally not databases designed to retrieve hard facts.
Right. They are predictive text engines designed to calculate and guess the most statistically likely next word in a sequence based on their training data.
But customer service is not a predictable statistical sequence of words. It is chaotic, highly specific, incredibly nuanced, and filled with bizarre edge cases.
Which makes algorithmic hallucinations not just possible, but statistically inevitable. When a probabilistic engine encounters a chaotic edge case, it doesn't understand. It doesn't admit ignorance. It mathematically invents a plausible-sounding sequence of words to fulfill its programming.
And the sources cite research indicating that in complex, multi-step customer service scenarios, the rate of hallucination can spike to over 25%.
25%.
That means 1 in 4 answers provided to a customer could be a complete fabrication.
The high-profile failures resulting from this are staggering, and they serve as massive warning signs for any CX leader. Look at the Air Canada debacle.
Oh, that was a mess.
The airline deployed a generative chatbot to handle customer queries on their main website. A grieving customer interacted with the bot to ask about bereavement fares, an inherently sensitive, emotionally charged topic requiring nuance.
Right.
The probabilistic chatbot completely hallucinated a fake policy, explicitly promising the customer a retroactive discount that absolutely did not exist in the airline's actual rulebook.
And when the customer later tried to claim the promised discount, Air Canada refused to honor it. and attempted a disastrous legal defense by arguing that the chatbot was a separate legal entity responsible for its own actions.
Which, from both a legal and ethical standpoint, is an absurd defense. The courts quickly ruled against Air Canada, firmly establishing the precedent that a corporation is entirely responsible for the information presented on its website, regardless of whether a human employee or an unsupervised algorithm generated the text.
And the consequences are even more severe when physical health is involved. Consider the case of NADA, the National Eating Disorders Association. In a bid for efficiency, they replaced their highly trained human helpline staff with an AI chatbot named Tessa.
It's just heartbreaking.
Almost immediately after deployment, Tessa began generating actively harmful, triggering weight loss advice to individuals suffering from severe eating disorders. The bot was advising vulnerable callers to track their calories and measure their body fat percentages. Nadia had to pull the bot offline immediately. It was a catastrophic failure of the technology to understand the context, the nuance, and the life or death stakes of the interaction.
These are not just unfortunate public relations blunders. They represent a fundamental systemic failure in operational strategy. When a company deploys raw, unguarded LLMs into the customer experience flow, they trigger a devastating economic paradox.
How so?
Well, the entire justification for deploying the AI was to radically reduce operational costs. Correct.
Right, deflect the tickets, lower the headcount.
But look at the internal data highlighted by Edge Tier and CMS Wire. Poor data integration, lack of context, and rampant hallucinations lead directly to a phenomenon known as recursive support costs.
Walk us through that.
A customer initiates an interaction with the AI bot. The bot confidently provides a wrong, useless, or hallucinated answer. The customer becomes incredibly frustrated, spends 10 minutes arguing with the machine, and ultimately demands to be transferred to a human agent anyway.
But now, the situation is exponentially worse.
Yeah.
The customer is furious, the core issue has been complicated by the bot's bad advice, and the human agent now has to spend twice as much time untangling the mess the AI created before they can even begin to solve the original problem.
Exactly. The company hasn't deflected a ticket. They have actively doubled the cost and time required to resolve it while simultaneously damaging the customer relationship.
The broader economic data backs this up completely. 55% of businesses now admit that making human employees redundant in order to rapidly implement AI was a strategic mistake.
Over half of them admit it.
Furthermore, according to Deloitte data cited in the Talon, one report, a staggering reality check has hit the market. Only 6% of organizations are actually seeing a positive return on their AI investments in under a year.
Only 6%. That completely shatters the narrative of instant frictionless ROI.
So I have to pose the ultimate question. If I am a customer experience leader, and the data overwhelmingly shows that my customers trust a human more than an AI, even in instances where the AI is mathematically correct, and I know the bot is highly prone to hallucinate, anger my customers, and ultimately trigger recursive support costs that destroy my budget. Why on earth am I deploying this technology at all?
You deploy it because the pressure from the board and the broader market to utilize the technology is immense, and frankly, because when governed and integrated correctly, it can provide profound operational value.
When governed correctly.
Yes. The solution is not to abandon artificial intelligence. The solution is to entirely abandon the reckless fantasy of unsupervised AI. This brings us to the core thesis of how successful organizations actually integrate these volatile models without destroying their brands or violating compliance. They do it by building a rigid, multi-layered assurance layer.
Let us break down this assurance layer, because as the sources make abundantly clear, AI governance is no longer a nice-to-have slide in a quarterly PowerPoint presentation. It is a strict, enforceable legal obligation. With frameworks like the EU AI Act establishing global precedents and the U.S. Federal Trade Commission launching aggressive initiatives like Operation AI Comply, regulators are actively hunting for algorithmic negligence.
You can no longer stand before a regulator or a judge and say, the algorithm made a mistake, it's a black box, we don't know why. Ed's Tier outlines a brilliant, highly practical framework for customer experience AI that consists of 4 distinct, mandatory lines of defense.
Let us walk through the mechanics of each line. Line 1 is pre-launch testing, commonly known as red teaming. This is where an organization actively attempts to break the model before it ever interacts with a real customer.
Yes, aggressive adversarial red teaming. You employ specialized teams to fire highly complex, emotionally charged, and deliberately confusing edge cases at the bot. You actively try to trick it into leaking PII, generating offensive content, or hallucinating a fake policy, and you adjust the base prompt until it holds firm.
But testing is never enough, which is why the second line of defense is arguably the most crucial piece of the architecture. Real-time safeguards.
Yes.
How do those real-time safeguards actually function? Because you aren't just letting the LLM connect directly to the customer's chat window, right?
Exactly the opposite. You must build a highly rigid monitoring layer, often consisting of smaller, specialized classification models that sits directly between the generative AI and the customer. This layer acts as a real-time policy trigger.
So what happens when it triggers?
If the LLM generates a response, the monitoring layer scans it in milliseconds before it is sent. If the response contains a sequence that looks like a credit card number or mentions a competitor's name, or if the system detects that the customer's input exhibits extreme anger or suicidal ideation, the policy trigger instantly catches it. It blocks the AI's output from ever reaching the screen and seamlessly, instantly hands the entire conversation over to a human agent.
It is an algorithmic kill switch. That is brilliant. Line 3 is post-interaction monitoring or automated quality assurance. The sources emphasize that you cannot just set an AI system and forget it, because models experience drift and prompts decay over time as public language evolves.
To combat drift, organizations utilize automated QA systems to continuously review hundreds of thousands of conversational transcripts. They are looking for subtle, creeping drops in factuality or minute shifts toward a more robotic tone. Crucially, they correlate those transcripts with customer satisfaction scores.
This allows the organization to detect patterns of failure and catch drifting behavior long before hallucination goes viral on social media.
Right. And finally, line 4 is institutional governance. This is the paper trail. It means maintaining highly auditable, immutable logs. It means strictly versioning your prompts so you know exactly which instructions the bot was operating under on any given day.
So if an FTC regulator knocks on your door to investigate a claim of algorithmic discrimination, you need to be able to pull the exact configuration, the exact training data parameters, and the exact safeguard logs from the specific day the incident occurred.
Yes. And the necessity of this strict governance brings up some incredibly profound philosophical points covered in the Said Business School source material. We have to discuss the application of Hannah Arendt's philosophy to artificial intelligence.
Hannah Arendt, wow.
Arendt as famously wrote about the dangers of bureaucratic obedience. She warned that monumental societal harm often originates not from active mustache-twirling malice, but from ordinary people passively obeying and deferring to opaque, complex systems without questioning them.
When applied to the modern corporate integration of AI, that concept manifests as automation bias. It is a vital and terrifying psychological insight. When an algorithmic system consistently appears to be faster, more confident, or more mathematically accurate than a human worker, the human develops a deeply ingrained psychological tendency to blindly defer to it. They stop scrutinizing the output.
They fall asleep at the wheel of the autonomous system. In what academics are now calling the algorithmic condition, humanity is navigating a world of distributed agency.
Distributed agency.
The AI is performing the calculation. It is predicting the likelihood of credit fraud, diagnosing a medical anomaly, or calculating the optimal route for a multi-ton vehicle. But the AI inherently does not care about the outcome. It possesses no skin in the game, no empathy, and no moral stakes.
Therefore, human beings must absolutely not allow themselves to become passive approvers of machine-generated outcomes. We must force ourselves to remain active, critical, and sometimes skeptical interpreters of the machine's advice.
This tension between machine calculation and human morality is perfectly vividly illustrated by the MDPI research paper discussing the classic trolley problem in the context of self-driving cars.
Right, everyone knows the philosophical dilemma. A trolley is hurtling down a track. Do you do nothing and let it hit 5 people, or do you actively pull a lever to switch tracks, saving the 5 but killing 1?
The terrifying modern reality is, how do you program an autonomous vehicle to make that moral choice in a fraction of a second?
Right. Do you hard-code the car with utilitarian programming, instructing it to always minimize total harm regardless of the action? Or do you use deontological programming, hard-coding the car to refuse to actively choose to harm a bystander, even if it means more total casualties?
It is an impossible ethical knot, and the fascinating reality is how the law is choosing to handle it. The EU AI Act, which serves as the leading global framework, completely dodges the substantive moral question.
They just bypass it entirely.
Completely. The law does not attempt to dictate which specific ethical framework a manufacturer must code into the vehicle. It realizes that a universal moral truth cannot be reduced to Python code. Instead, the legislation mandates strict procedural safeguards.
Procedural safeguards meaning what exactly?
It demands absolute mathematical traceability, multi-layered decision logging, and robust human oversight mechanisms. The law focuses entirely on ensuring that after the machine makes a decision, a human being can audit the logic, understand the variables, and ultimately bear the legal and moral responsibility for the outcome.
It fundamentally all comes back to human accountability. And that is why the overarching strategy proposed by Capgemini and the sources is so deeply resonant. Human-led, AI-powered, it is a clear delineation of duties. Artificial intelligence should be aggressively utilized to handle speed and scale. It should be used to summarize 50 pages of dense policy documents in a microsecond, or retrieve a lost tracking number instantly from a massive database. But humans must fiercely retain control over the emotionally charged moments, the complex, nuanced negotiations, and the ethical judgments where human vulnerability demands authentic human care.
If we pull all of these disparate threads together and connect them to the broader macroeconomic picture, it is clear that the entire corporate landscape is undergoing a massive correction.
A huge correction.
The last 3 years were defined by a frantic, often reckless dash to automate everything possible in a desperate bid to cut overhead costs. The next decade will be defined by the painful realization that over-automation creates immense systemic fragility, massive legal liability, and irreversible brand destruction.
Right.
The most successful, enduring companies of the future will not be the ones that automate the highest percentage of their workforce. They will be the ones that govern their AI the most rigorously.
That is an incredibly powerful summation of the entire landscape. So let us synthesize this massive journey for you, the listener. We have covered an immense amount of technical and strategic ground today in this deep dive.
We really did.
We started by looking at the foundational architecture, exploring how AI completely explodes the traditional security perimeter, creating a porous environment where shadow AI and API model extraction threaten to leak a company's deepest intellectual property.
We then explored the intense regulatory tightrope of data minimization, diving deeply into the mechanics of feature selection, mathematical perturbation, synthetic data generation, and federated learning.
Yes, and we examined how protecting a model against overfitting is the absolute key defense against devastating model inversion and membership inference attacks. We looked at the terrifying physical vulnerabilities of sensory models, from adversarial pixel patches tricking autonomous stop signs to malicious high-frequency audio attacks targeting voice recognition systems, and how defenses like FSAT try to isolate those threats.
And finally, we waded into the customer experience disaster zone, seeing firsthand how deploying raw, hallucination-prone probabilistic engines to save a quick buck ultimately results in recursive support costs and shattered consumer trust.
The absolute through line of everything we discussed today, the non-negotiable imperative for modern business, is rigid, structured, human-in-the-loop governance.
Because the technology is extraordinary, but it is fundamentally incomplete without the human element acting as a safeguard.
So, to you listening right now, whether you are a backend developer writing the code, a compliance officer auditing the data pipelines, or a CX leader managing a sprawling customer service team, your ultimate competitive advantage in this new era is not deploying the biggest, most expensive model. It is treating artificial intelligence as a conversational partner, a highly capable, incredibly fast, but fundamentally flawed and gullible assistant, rather than treating it as an infallible oracle. You have to maintain your critical thinking.
And I would like to leave you with one final provocative thought to mull over, building directly on that idea of critical thinking and human oversight.
Let's hear it.
We have spent this entire hour discussing how to mathematically train AI to act more human, teaching it empathy, ethics, and nuance, and conversely, we have discussed how to build massive infrastructure to protect humans from the dangers of AI. But consider this concept, drawn from the Said Business School research. As we increasingly enthusiastically rely on AI to draft our delicate emails, to summarize our complex, nuanced meetings, and even to apologize to our frustrated customers on our behalf, are we risking a societal cognitive atrophy?
Cognitive atrophy.
If we continuously outsource our communication, our conflict resolution, and our fundamental critical thinking to a machine, what happens to our own innate capacity for empathy and moral judgment a decade from now?
That is a heavy, necessary question to carry with us as we navigate this transition. Thank you so much for joining us on this journey today. Keep questioning the systems around you, keep learning, and we'll see you next time on The Shifted Ledger.